In the last topic of the network models, I'm going to talk about network simplex method. This presentation corresponds to the material on your textbook, section 8.7. So the network simplex method is used to solve the minimum cost network flow problems, which has been introduced in section 8.5. Now let's see how this method works. Now these are the 4 steps in a network simplex method. We will go through each of these steps one by one, but now let's take a look at the highlights of each step. In the first step, we need to determine a starting BFS, basic feasible solution. If you can recall, this is a very typical thing to do in any simplex method. In the original simplex method, you transform the linear programming problem into a standard form by adding slack, excess variables, and artificial variables if necessary, and then you get a starting BFS that you can put on a simplex table and start doing all the iterations. If you recall about transportation simplex, this is also the starting step of simplex transportation, in which you may use one of those 3 methods, northwest corner method, minimum cost method, or Vogel's method to obtain a starting BFS. So really this is the same thing for all the simplex method, including this network simplex method. We need to find the starting BFS, which we can start from there and then improve the solution until we get the optimal one. And then in the second step, the keywords here is that we need to define which variables are the basic variables, which variables are non-basic. Once we have done that, we need to know if this current BFS is not optimal or not. And then in step 3, this is specific to this network simplex method, we need to identify a cycle. This cycle will be used to improve the current BFS if it's not optimal yet. And finally, once we have identified that cycle, we perform some procedure such that we can obtain the new BFS, which is an improvement from the previous one. And then we keep doing this, repeating this until we reach the solution that we can say that, okay, this is an optimal solution. So after step 4, you see that we go back to step 2 and just keep repeating these steps until we can say that current BFS is optimal. Now let's take a look at an example of a minimum cost network flow problem. We're going to solve this problem using the network simplex method. Now the objective function of this problem is that we're going to minimize the total cost of all flows that are flowing through this network. So for example, this number 10 here, it corresponds to the cost of transporting 1 unit of flow from 1 to 2. So 10 is the cost of transporting 1 unit of flow, and then x12 is how many units of flow that you send from 1 to 2. Let's take another example. Let's say this here, $6. It is this 6 here. So for each unit of item that you send from 2 to 5, it will cost you $6. So $6 is the cost, and then x25 is the number of units that you are transporting from node 2 to node 5. Now the other number above each arc, like this 5, 6, and so on, it shows the capacity of each arc. So for example, the arc from 1 to 2, it has the lower bound of 0, it has the upper bound of 5. And then from 2 to 5, the lower bound is 0, the upper bound is 6. The lower bound is 0 because you cannot flow negative amount of something. So For each arc, if you want to use that arc, the lower bound is 0, means you're transporting nothing through that arc, and the upper bound is the capacity of each arc. Now remember that in the minimum cost network flow problems, we need to determine the flow balance constraint for every single node in the network. So here are the constraints. So the first constraint is for node 1. You see that from node 1, the outgoing arcs are 1 to 2, outgoing 1 to 3, and then outgoing 1 to 4, must equal to the net supply of that node. And then you see this value here, it shows the net supply of this node. It means that node 1 can supply 10 units, and it is its net supply because it only has outgoing arcs, so it can send out 10 units amount of flow at a period of time. For the other nodes, you don't see any value here, so it means that node 2, 3, and 4, their net supply equals 0. It means that whatever they receive from the incoming flow, they should send them all out in the outgoing flows. So let's see node 2. The outgoing flows from node 2 is 2 to 5, so it is positive. And then the incoming is from 1 to 2 and from 3 to 2. Those are negative in signs because incoming has a negative sign and then outgoing has a positive sign. For node 3, the outgoing flows are 3 to 2 and then 3 to 5 also outgoing, and then 3 to 4 also outgoing, and then the incoming is x13. For node 4, the outgoing arc is from 4 to 5, and then the incoming arcs are coming from 1 to 4, and then from 3 to 4. Finally, for node 5, all arcs that are related to node 5, they are all incoming nodes, bringing inflows. So all the signs are negative from 2 to 5, from 3 to 5, and then from 4 to 5. The net supply for this node is minus 10. It means that it only receives 10 units of flows, and then it doesn't send out to any other node. So it only receives inflows, but it doesn't have any outflows. So this is how you read all the data that is given in this figure and then translate it into a formulation. The first step in the network simplex is determining the starting BFS. So if we have n nodes in our network, it means that we have n conservation of flow constraints, which means that for each node that we have, we need to make sure that the flow equals to the net supply of each node. So in this example, if we have 5 nodes, it means that we need to have 5 constraints, one for each node, to make sure that the net supply for each node is satisfied. However, it turns out that if we satisfy n-1 constraints, the remaining one is automatically satisfied, which means that if you satisfy the constraint for the net supply in node 1, 2, 3, and 4, it means that automatically the net supply constraint or the conservation of flow constraint for node 5 is automatically satisfied. It means that even if we have n constraints, we can ignore one of them, such that if we only have n-1 constraints in our BFS, we also only need n-1 basic variables. If you recall, in the original simplex, the number of basic variables that you have equals to the number of constraints. Here in this problem, because we can ignore one constraints, so originally we have n, but we can ignore one, So finally, our basic variables, the number of basic variables also n minus 1. So it's a good start. We know that to have a basic feasible solution, we need to have n minus 1 basic variables. To have a basic feasible solution, we know that we need to have n minus 1 variables, with n is the number of nodes that we have in the network. Okay, so we know that we need to have n minus 1 variables. But how can we tell? How can we tell whether a variable is a basic variable or is it a non-basic variable? In the case of network simplex method, a variable is a basic variable when its value is in between the lower bound and upper bound. So to be a basic variable, the value must be in between. Because if the value of a variable equals the lower bound, it is a non-basic variable. If the value of a variable equals to the upper bound, it is also a non-basic variable. So the only way for a variable to be a basic variable is that its value must be in between the lower bound and the upper bound. Now let's take an example to make it clear. Suppose we're talking about x12, which is the number of flows that we send from 1 to 2. We see that here the capacity of this arc is 5, so the upper bound for this variable x12 equals 5. The lower bound of x12 is 0. Remember, because we obviously cannot transport negative unit of flows through any arc. So here x12, the number of units that we can send from 1 to 2, has the lower bound of 0 and upper bound of 5. Now look at some possible cases. If the value of x12 is in between the lower bound and upper bound, x12 is a basic variable in that kind of solution. Suppose we have another solution in which x12 equals 5, which means that we are sending 5 units of flow from 1 to 2. In that kind of solution, x12 is a non-basic variable. Let me repeat. In that case, x12 is a non-basic variable. Now, look at the third possibility. Suppose we are sending nothing from 1 to 2. So there's nothing that is flowing from node 1 to node 2. It means that x12 equals exactly 0. In this case, again, x12 is a non-basic variable. So we have looked at several possibilities of solution with regards to the value of x12. And then if the x12 equals exactly the lower bound of the arc 1, 2, or exactly the same with the lower bound of the arc 1, 2, it means that x12 is non-basic in that kind of solutions. However, if x12 takes the value in between 0 and 5, in that kind of solution, x12 is a basic variable. Combining those two information, now we know that in order to have a basic feasible solution, first we need to have n minus 1 basic variables, and then second, each of those variables must take the value in between the lower bound and the upper bound. And the third requirement is that those n minus 1 basic variables, they must form a spanning tree. So let's take a look at the example that we have earlier. Now we try to find a basic feasible solution for this example. So suppose this is a basic feasible solution. Let's check all the requirements that we have. This solution have n minus 1 basic variables: x13, x35, x25, x4, 5. And then let's check the value. The value here is 1. It is in between the lower bound of the arc 1, 3, which is 0, and also below the upper bound of arc 1, 3, which is 3. So this is good. And then from 3 to 5, the value is 1. 1 is in between the lower bound of arc 3, 5, which is 0, and the upper bound of arc 3, 5, which is 5. Remember that the lower bound of each arc equals 0 because you cannot transport a negative unit of flows. Okay, so the lower bound is 0 because you cannot pass the amount of negative unit of flow. It just doesn't make sense. And then the upper bound for each arc is the maximum capacity of each arc. Okay, so here, like you're sending 5 units from 2 to 5, x to 5 is a basic variable because this 5 is in between the lower bound of this arc, which is 0, and below the upper bound of this arc, which is 6. And then x for 5 equals 4. 4 is in between the lower bound of this arc, 0, and the upper bound of this arc, 6. And then this is also a spanning tree because we have 5 nodes here, but we have only 4 arcs, 2, 3, 4, and it contains no loop. So this is a tree. Now this figure has shown the basic variables, but what about the non-basic variables? So to complete the basic feasible solution, or BFS, we need to draw the non-basic variables at the upper bound using dashed arcs. So think about it. If you have a flow of 5 going from 2 to 5, where does this 5 comes from? It should come from here, right? Otherwise, how can you send something from 2 to 5 if nothing goes into 2? So try to look at the original problem here, and then you see, hey, exactly this is 5. So it will match if let me erase this first because erase this first and then use the correct symbol. So you say that, okay, if I send 5 units of flow, it is exactly correct to be passed through from 2 to 5 later. And then same things happen here. You have 4 units of flow going from 4 to 5. But where does this 4 units come from? And then you check here. Suppose you send 4 units from 1 to 4. It exactly matches what you want. So this is how you complete the non-basic variables. Now let's talk about this again. Why this x1 to equals 5 is a non-basic variable? Because 5 here is exactly at the upper bound of arc 1, 2. Arc 1, 2 has the maximum capacity of 5. Let me erase this a bit. So you see that x1, 2 has the maximum capacity of 5. And then here you're sending 5 units. So it's using all the capacity from 1 to 2. So x1, 2 is a non-basic variable. The same reason for x1, 4, you're sending 4 units. And then the maximum capacity of this arc from 1 to 4 is also 4. So this is a non-basic variables. And then what about the other, like x32? It is also a non-basic variable because x32 equals 0. So it is a non-basic variable. x34 is also a non-basic variable because you're sending nothing from 3 to 4. So x34 is at the lower bound of the arc of 3 to 4. That's why x32 is a non-basic variable. x34 is also a non-basic variable. So up to now, we have done step 1. We have got a starting BFS And then we have got the n-1 basic variables with this solid arcs. And then we also have the non-basic variables at the upper bound denoted by dashed arcs. See that you do not need to draw any non-basic variables at the lower bound. You only need to draw the non-basic variables at upper bound. Okay. And then if you ask, how can you find this kind of basic feasible solution? Well, the textbook says that it's often found by trial and error. So you really need to think about, okay, let's try to make a tree, and then let's try to think about which non-basic variables at the upper bound, and so such that your tree is still, you still have the tree that you want, but then all the non-basic variables at the upper bound, they also match with all the flows that should go from here, like 4 to there, 4 and 4, then from here to there, 5 to 5, and also satisfy this, the net supply of node 1 is 1, the net supply of node 5 is minus 10, which means that node 1 must send out 10 items, and then node 5 must receive 10 items. Okay, I know it's not easy, but the textbooks say that this should be done by trial and error. Now we can go on to step 2, in which you are going to compute the row 0. So if you recall in the original simplex, when you have a table and then you want to tell whether the current solution is optimal or not, you need to look at the row 0, the topmost row on your table, right? By looking at that row, you can tell whether you need to do another iteration or the current solution is already optimal. Since we don't have any kind of table in network simplex method, let's see how it works here. So we saw earlier that for each node that we have in the network, we need to define a conservation of flow constraints or a flow balance constraints. But we also talk about that if we have n nodes and then we satisfy only n-1 of them, the remaining one is automatically satisfied. In other words, if you have n nodes in the network, you can arbitrarily drop the constraint of any one of them. So for example, you just drop node 1's constraint. Now, if you recall, when you want to construct a simplex table, you can do it from this kind of formulas. You require CBV B inverse to construct the row 0 of a simplex table. Now in this case, we just saw in step 1 that we need n-1 basic variables. And then also it is because the fact that we can only consider n-1 constraints. So in our CBV B inverse for this kind of problem in the network simplex method, we only have n-1 components. Suppose we drop node 1 constraint, so we have y2, y3, and yn. So how do we compute y2, y3 up to yn, and what are these y? Well, we are not computing them, we simply define them. So we define that, suppose we have CBV B inverse, and then we just define the content of the CBV B inverse is y2, y3, and yn. Again, we are not computing them, we're just defining. We define that we have CBV B inverse and these are the contents. Okay, and then how can we use this CBV B inverse? Recall again from chapter 6 in your Wayne Winston's textbook, when you want to compute the coefficients of a variable in row 0, you use this formula. CBV B inverse times Aij minus Cij. So Cij with this flat line or flat hat above the C means the coefficients of that variable that you see on the table. And this C without any hat, without any line above the C, it means the coefficient of that variable in the original problem. So in the objective function, if you see like 10 times x12, that 10 is this thing. But if you want to know the coefficient in row 0 for x12, it is denoted by this thing. Okay, so if you got confused about those symbols and the difference between the coefficient in row 0 and the coefficient of that variable in the original problem, you need to go back to chapter 6 to think about it, okay? Now we're going to use that formula to compute our row 0. I know I've said earlier that we don't actually have the physical table like the original Simplex, but we're still using that kind of analogy to help us to determine whether our basic feasible solution is already optimal or should we do another iteration. Now let's see how we can apply this formula to the BFS that we've got in step 1. So this is the BFS that we've got from step 1. In this problem, we have 5 nodes. So we have 5 constraints, 5 equations that shows the constraints of conservation of flows. Now remember what I said before in the previous slide. In this problem, we can just discard one of the constraints. And suppose again, we're discarding the constraint for node 1. So now we're left with just 4 constraints. Again, we can do this because if we satisfy these 4 constraints, the first one is automatically satisfied. Now let's apply this formula here to compute the coefficient of x35 in row 0. You can notice here that x35 is a basic variable. See, the arc is a solid arc, so x35 is a basic variable. So we're going to compute the coefficient of x35 in row 0. We expand this equation. CBV B inverse. From the previous slide, we defined the CBV B inverse to be like this. Again, we are not computing CBV B inverse. We simply define the CBV B inverse equals y2, y3, y4, and y5. And A35, we can get this value using the coefficients of x35 in the constraints. So you don't see x35 here, so the first value is 0. You see x35 here with the coefficient of +1, so you see 1 here. There's no x35 there, so 0 again. x35 here has the coefficient of -1, so that is -1. Okay, so that's how you get A35. Let me erase this a bit to make things not too messy. And then finally for C35 here, you can check the original problem and then you can see that the cost of transporting 1 unit of flow through the arc of 3,5 equals $7. So now you just multiply this using vector multiplication. Y2 times 0, y3 times 1, y4 times 0, y5 times 1. You get y3 minus y5 minus 7 equals 0. Now I haven't talked about why the left-hand side is 0. Can you guess why? Again, if you recall a simplex table, if a variable is a basic variable, what is the coefficient of this variable in row 0? The answer is 0, right? Basic variable in a simplex table always has the coefficient of 0 in row 0. So many zeros to say, right? Again, let me repeat. For a basic variable, the coefficient of that variable in row 0 is 0. Okay, finally, we can simplify our computation to look like this. Y3 minus Y5 equals 7. So we can generalize to say that for the case of basic variable, yi minus yj equals cij. Cij without the hat, because cij with the hat equals 0 and we already throw it out from our computation. Not really throwing it out, because anything 0 will just will not appear in the computation. And then for the non-basic variable, we just take this row as analogy or idea, and then we can conclude that for non-basic variables, Cij with hat equals yi minus yj minus Cij without hat. Now, why we cannot throw this out? In the basic variables, we can set Cij with hat equals 0, but in non-basic variables, why we can't do the same thing? Again, remember in a simplex table, the one that has coefficient of 0 in row 0 is only for basic variables. For non-basic variables, the value can be 0, but we cannot say for sure that the coefficient must be 0. Okay, that's why we cannot set any value for this Cij with hat in non-basic. For basic variables, the coefficient of that kind of variables in row 0 must be 0. Okay, so now we have got these relationships for basic variables and for non-basic variables. Next, we are going to see how we can use all these two formulas to determine whether our current BFS is optimal or not. Now finally, we're arriving at the most important question in step 2. Is the current BFS optimal or not? If the current BFS is optimal, it means that the basic variables are already good. We do not have to replace them. However, if we know that the current BFS is not optimal, it means that we need to take one basic variable out from the BFS and then replace it with another variable which is currently a non-basic variable. That's how the simplex works, right? You take one basic variable out, you take one non-basic variables in, and then you check again, is it optimal? If not, you repeat the same thing, take one basic variable out, take one non-basic variable in to become basic variable. That's what we're going to do here. So we're going to check whether the non-basic variables can be taken in to BFS to replace any of the basic variables. To check that kind of possibilities, we need to look at the non-basic variables at lower bound and at upper bound. Remember, in network simplex method, the non-basic variables are the variables at the upper bound and at the lower bound. If a non-basic variable is currently at the lower bound, the current BFS is optimal if the C hat for those kind variable less than or equals 0. For the variables at upper bound, the current BFS is optimal if the Cij hat for these kind of variables is already greater than or equals to 0. To make the current BFS optimal, these both conditions must be satisfied for all non-basic variables. If there is any basic variable that does not satisfy either this or that condition, it means that the current BFS is not optimal. And that non-basic variable becomes the candidate to go into the BFS to replace one of the basic variables. Okay, so let me repeat. If you saw any non-basic variables does not satisfy either this or that, it means that the current BFS is not optimal. And that non-basic variable is the candidate to go inside the BFS, replacing one of the basic variables that is currently in the BFS. Now let's take a look at an explanation of what we just saw in the previous slide. So the problem that the network simplex method is trying to solve is a minimization method. It's the minimum cost network flow problems. So first, let's take a look at the non-basic variables at lower bound. If you recall the simplex table for a minimization problem, you will say that the table is already optimal if all the coefficients in row 0 is already less than or equal to 0. Right? Think about it for a few seconds. What does this actually mean? It means that for all non-basic variables which are currently at lower bound, whenever we try to increase their value, we will make the objective function value worse. So we cannot increase any of the non-basic variable when we already have this kind of condition. If the C hat is, let's say, negative for non-basic, and then we raise the value of that non-basic variable, our Z value will become larger. For minimization method, it is something bad. So we must not do that if we are already at this condition. Now, the opposite is true for the non-basic variable at the upper bound. If we are already at this condition and the non-basic is at upper bound, if we try to decrease the value of this non-basic from upper bound to something smaller, then our objective function value will become larger, which is worse in terms of minimization, so we cannot do that. It means that anytime we have this condition for non-basic variables at lower bound and this condition for non-basic variables at upper bound, we are already having a current BFS is optimal, which means that if it's not satisfied, any of this is not satisfied, it means that, as I said before, our current BFS is not optimal. So you've seen really that the key is to find the Cij hat for each of the non-basic variable. Okay, let's practice the formulas that we've seen before. For basic variables, we're going to use this formula. Yi minus yj equals Cij. First, set y1 equals 0. Why? Because remember we just dropped one of the constraints arbitrarily, one of the conservation of flow constraints arbitrarily, so we set y1 equals 0. Now we can compute the values of the other y's using the basic variables that we have from the BFS that we've got from step 1. So here the basic variables are x1, 3. So here 1, 3. You notice that? And then let's say x2, 5. So y2 minus y5. x3, 5. So here you have 3 and 5. x4, 5. So you have y4 minus y5 equals to the Cij. So this is C13. You need to see this the C13 from the original problem. This is $12 to transport 1 unit from 1 to 3, from node 1 to node 3, I meant. And then you also need to check all this Cij without the hat from the original problem, okay? I mean from the original figure. This BFS does not show the cost of transporting each unit of flow from one node to the other. Okay, so you have these equations here, and then you just solve them by starting with this y1 equals 0, and then plug 0 into this equation. You get y3 equals to minus 12, and then so on and so on until you get the values for all y's. The purpose of this y's is to compute the c hat of all the non-basic variables. So the non-basic variables that we have here are, let me erase things a bit to make this look less messy. Good. So the non-basic variables are x12 at upper bound, x14 at upper bound, x32 at lower bound, and then x34 at lower bound. So we need to compute the Cij hat for those variables. So this is C12 hat. Use this formula. 1, 2 means y1 minus y2 minus C12. And then for this C14 hat, y1 minus y4 minus C14. And then do the same for C hat 32 and C hat 34. And now it's the time to check whether any of these non-basic variables violates the requirements to say that this BFS is already optimal or not. So let's check this one by one. 1, 2, and 1, 3, they are at upper bound. So this is at upper bound, this is also at upper bound. If they are at upper bound and the coefficient of C hat is positive, it is okay. Now C32 indicates X32, it is currently at lower bound. So let me change the color. So this is at lower bound, and then X34 is also currently at lower bound. To make us possible to say that this is optimal, we need to have this coefficients to be less than or equals to 0. This is okay, but here you see it is not less than or equal to 0. So which means that among the non-basic variables, one of them violates the optimality condition. So it means that this BFS is not optimal yet. Based on our computation of the C hat, we have finished the step 2. So we have calculated all the y's. Remember to set y1 equals 0. And then we have also compute for all non-basic variables. We have computed the C hat ij. And then we have checked the optimality condition for non-basic variables at lower bound. This must be satisfied. And then for non-basic variables at upper bound, this must be satisfied. And then based on the previous slide, we saw that one of the non-basic variable violates the optimality conditions, which is corresponds to the variable of x34, which is currently at lower bound. So it means that currently the flow from 3 to 4 equals 0. Nothing flows from 3 to 4. Based on this calculation, we know that we need to try to increase the value from 0 to something positive. So that's what we're going to do in step 3. So up to this point, we have finished step 2 with the conclusion that the BFS that we have obtained in step 1 is not optimal yet. We have also seen that the non-basic variable x34 must be increased from the current value, which is 0 at the lower bound. So I'm going to talk about how we can perform step 3 and step 4 in the next video. So see you in the next video. Thank you.